Okay, so far we have learned how to do a series circuit and we've learned how to do a parallel circuit. But what happens if we have a combination series parallel?
Like that. It doesn't look healthy.
Okay, so both of these are 300 to the left here. And then we have 1, 2, 3. We have a 2 and a 3. And we have a 40. To solve these, we follow a couple simple steps. The first step is we want to find the effective resistance of the parallel part. Then we want to solve the theory. And 3, we want to go back and find the current through the parallel part.
Two bricks, parallel.
Don't have trouble getting you on but
You work there?
Okay, so how do we find the parallel part's effective resistance? Exactly, we have to do the 1 over R formula. So if we do 1 over 200 plus 1 over 300, 200 to the minus 1 plus 300 to the minus 1 equals to the minus 1. And we find that this section acts like it's 120. So 40 still acts like it's 40. Then we add 100, 200, 300. So if we have 100 to the minus 1 plus 200 to the minus 1 plus 300 to the minus 1 equals to the minus 1. we find that this section acts like it's 54.5. And then if we have two 300s added together, which is 300 to the minus 1 plus 300 to the minus 1 equals to the minus 1, and you say, hey, that just splits the difference at 150.
Bless you.
So that was number 1 in blue.
Why don't we include the 40 ohms resistor?
Because that was in parallel with nothing.
It's a good question.
Did you include the 200 and the 200, 100, 300? Yes, sir.
Yes.
Everybody understand step 1?
Yes, sir.
Super simple, right? So now we go to step 2 and we say, okay, in step 2, we are going to just solve it like it's a series circuit. So now we say, okay, when we're solving like it's a series circuit, first we find the effective resistance. So to find the effective resistance around the series circuit, all we do is add the resistors all the way around. So here we're going to say I have 120, and I have 40, and I have 54.5, and I have 150. Right? So that gives me an effective resistance of
Hmm.
364.5. So the effective resistance of the entire circuit is, first you gotta find the effective resistance of each part that's in parallel, and then you just add them up in a circle. And you find that super simple. Second step in any series problem is once you find the effective resistance, you find the current, which is the same everywhere. So the current is just gonna be the total voltage over the total resistance. So we're gonna have our 42 volts over 364.5. And you're gonna get 0.1152. The third step whenever we're going in a series circuit is we find the voltage drop in each section. And we do the voltage drop in each section just by doing V equals IR. So since the current is the same everywhere, then the current is going to be the same everywhere.
Thank you.
And we get 0.1152 times the first section, which was 120. And then we get 0.1152 times the second section, which was 40. And 0.1152 times the third section, which was 54.5.
That's it.
And we get 0.1152 times the fourth section, which was 150.
Split it up. Each one, 2 CP.
And then when we double check that, that should add up to what?
42.
What does it add up to?
Something close to 40.
13.8 plus 4.6. Hey, that came out exactly right. Now, does it always come out exactly right? No, sometimes you're gonna end up with 41.9 as a rounding. Okay, so that's the end of step 2. Then we go to step 3 over here and we say, okay, step 3 was we want to find the current through the parallel parts. Well, first of all, I don't know what the current is through each individual part, but I do know the current going here through 40 has to be the total current, right? So then we look and we say, well, okay, in this section, since these two are equal, then that means half the current's going to go to the right and half the current's going to go to the left. So all I have to do is take this amount and divide it by 2. The other way you're looking at that is you're saying, well, what is the voltage drop across each section? Well, I know if I have a voltmeter that's right here that's measuring across here, this first section we just figured out, it's going to lose that much voltage, right? So to find the current through each individual branch, this is going to take clearly the smaller resistor is going to take more current, so it's going to take basically 3/5 of it, right? And this one's going to take 2/5 of it, but all you got to do is plug into V equals IR, solving for I. So if we solve for I, V equals IR, R comes over yonder. So the V has to be not the total voltage of the thing, but the total voltage of that second. This voltmeter, of course, would read 13.8. So if I have 13.8 divided by 200, and I have 13.8 divided by 300, those will tell me how much is going through each branch. Or like I said, you can take the total branch and you can say, well, out of the 500, I'm going to have how much over here? 3/5 of it over here, and I'm going to have 2/5 of it over here. It'll work out the same way. That's what's fun about that. So you're going to have 13.8 divided by 200, gives me 0.069. And 13.8 divided by 300 gives me 0.046. And again, what should these two add up to if we add them together?
Total
1.1152.
Hey, what do you know? If we add them together, we get. Which is what we were getting. So. So for the 40, of course, it's just going to be 0.1152. In the bottom section here, we have a 100, a 200, a 300. The ratios get a little harder, so again, it's easier to just say I is equal to V over R. So what is the V in this bottom section?
6.3.
That's going to be 6.3. So if I have 6.3 divided by 100, I'm going to have 6.3 divided by 200, and I'm going to have 6.3 divided by 300. If we add all those up together, we get 0.1155. And again, it's a little bit off because of rounding. If we would never round anything, it would come out perfect. But that would drive you crazy writing down all those numbers. So for this last section again, what we can do is we can say the total voltage drop in this section is the 17.3, and then we can divide it by 300, or we can just say, hey, since these two are equal in magnitude, then it's going to be a nice 50-50 split here. So that's going to be the easiest way. We're just going to take the 1152 divided by 2, and that's going to go in half and in half.
Mr. Paulson, for the other one, how do you know which one belongs to which one? Like the one with 3?
Well, the 100 would be this one, so that would be what was going in the top. But again, you should notice that the smaller resistor has the biggest current and the biggest resistor has the smallest current.
Yeah, that should make sense.
So, yes, that means the current here is 0.0576 amps. So here and there. Totally logical, right? That's why we love this.
Yes, we love